Okay, so now let me talk about polynomial interpolation. And let me state the problem as follows. Okay, so I'm given n plus 1 distinct points. Let's say x0, well, they're distinct, x, so I'm going to order them x0 to xn. Okay, and I want to find Pn of x, which is a polynomial of degree less than or equal to n. It's like int variable x. Okay, so this statement is that it's a polynomial of degree less than or equal to n. Okay, such that f at xi is equal to Pn at xi, and this is true for I equals to 0 all the way up to n. Right, so let's think about that for a second. Right, you have n plus 1 points. A polynomial degree less than or equal to n has n plus 1 coefficients. So you have basically n plus 1 constraints and n plus 1 unknowns. So that's, you know, at least in principle, it's like a potentially solvable situation. Okay, so let's try to use the interpolation condition to derive it's like one of these interpolating polynomials. Okay, so let's look at an example. N equals to 1, so this is linear interpolation. Okay, so I'm given x0, f at x0, and x1, f at x1. And I want to find p1 of x, which is a plus bx, okay, with the property that p1 of x0 is f at x0, and p1 at x1 is f at x1. Okay, so I can write this in the following way. Okay, I can write this as p1 of x is a polynomial which looks at like the form x minus x1 over x0 minus x1 times f at x0 plus x minus x0 divided by x1 minus x0 times f at x1. Okay, all right, so I'm going to look at these two polynomials, which are, you can check that they are polynomials of degree 1, and they have the following property. Okay, so this is equal to 1 if x equals to x0, and 0 if x is equal to x1. This thing is equal to 0 at x equals to x0, and 1 at x equals to x1. So, all right, so in general then, if you want to satisfy some sort of interpolation condition, what you need to do is you need to be able to construct these polynomials with the property that they're 1 at a particular point out of those n plus 1 distinct points, and 0 at all the rest of the points, right? That's basically the construction which we have here. Okay, so these have special names. These are what are called the Lagrange polynomials. So I'm going to write this first one as L1 comma 0 of x. This is equal to x minus x1 divided by x0 minus x1. And then this is L11. So L11x is equal to x minus x0 over x1 minus x0. Okay, so these are called Lagrange polynomials. And my claim is that they are uniquely defined by these conditions. Okay? All right, so let's try to generalize these Lagrange polynomials to higher degree. And so let me state a definition for you. So the Lagrange polynomial L n j x has degree n and satisfies the following property, that L n j at x I, okay, is equal to 1 if I is equal to j, and 0 if I is not equal to j. Okay. All right. So the claim is that with these properties, you then have a unique expression for what the Lagrange polynomial has to be. And the way you see this is basically through the fundamental theorem of algebra, right? So if you have a polynomial of degree n, the condition that it vanishes for all I not equal to j means that I know n roots, right? So I have the n roots of this polynomial. So that means that this polynomial is defined up to a constant by just its roots, okay? So let's see where we go with this, right? So that's saying that, so we have, so Lnj has roots at x0, x1, all the way up to x j minus 1, xj plus 1, all the way up to xn, right? So they have n roots, okay? So then by the fundamental theorem of algebra, right, it has to be that L n j x, right, is some constant times the product of linear factors x minus xi for I not equal to j. Okay? All right, so I've used the condition where it's 0, and I have one additional condition, which is that it's 1 if I is equal to j, right? So Ln j xj is equal to c times the product I not equal to j of xj minus xi. But this is equal to 1, which means that c is equal to 1 over the product I not equal to j of xj minus xi, from which, right, I can compute what this Lagrange polynomial is, right? So that means that Lnj of x is this product of I not equal to j of x minus xi over xj minus xi. Okay, and then this denominator is never 0 because we have assumed that the points are all sort of distinct, right? Okay. So, all right. So that's one observation. And then the claim is that, and this thing has a property that Lnj xi is equal to 1 if I is equal to j, and 0 if I is not equal to j. Right, so this statement is equivalent to this. Well, this together with the condition that Lnj is a polynomial degree n, right, uniquely specifies this expression. Okay. And if you've never seen this pi notation before, it means that I take the product of all of these terms, right? It's a little bit like the sum, sort of the sigma notation, where I sum all these terms. So here I have a bunch of different terms. I just take the product of all of them. Okay, all right. So once you have that, if you want to construct an interpolating polynomial, then given sort of the Lagrange polynomials, right, we can construct a Lagrange interpolating polynomial as follows. Okay, so Pn of x. So I want Pn of x to agree with f at points x0 to xn. Okay, so Pn of x is going to be the sum from j equals to 0 to n of L n j of x. Okay, so this is a polynomial degree n times f evaluated at xj. So this is just a number. Okay, so the claim is that this thing. So the claim is that Pn of x is Pn of xi is equal to f of xi. Okay, and the way you see this is just following the definition. So Pn of x I is equal to the sum from j equals to 0 to n of ln j xi times f xi. But this thing here is equal to 1 if I is equal to j and 0 if I is not equal to j. Right? So if I evaluate xi, the only term it's like which is non-zero is I is equal to j. Okay, and all the other terms vanish, so that's equal to just 1 times f at xj, which, sorry, f at xi. Okay, so j is equal to I. Sorry, that's a j here, right? So, okay. So the only time this is non-zero, and in fact it's 1, right, is when I is equal to j. So that's 1 times f at xi. So this is just f at xi. Okay. So anyway, so this this property here is what is oftentimes referred to as the Kronecker delta property. Okay, so the Kronecker delta property, right, guarantees that when you have this sum, it collapses to just one term, which is when I is equal to j, right? So that gives me just f at xi, which is what we want. Okay. All right. So that is indeed a Lagrange interpolating polynomial. Okay. So so let me say briefly a bit about the advantages and disadvantages of this. Okay. So the advantages are that the derivation is straightforward. And it has theoretical value in the sense that we'll use it to prove a bunch of things. And the third thing is that if you fix the interpolation points, so if x0, x1 to xn are fixed, that means that these Lagrange polynomials are the same, and it's easy to apply, it's like that interpolant to other function values, right? So if the x0 to xn are fixed, then the function values sort of can be easily changed. Okay, and then the disadvantages. Are that it is cumbersome to evaluate. And what I mean by that is that if you look at trying to evaluate that interpolating polynomial, each of those terms don't really lend themselves nicely to, say, using Horner's method to speed up the evaluation. Okay, so this is very inefficient in terms of the number of operations. Okay. And the other thing it's like, which is unfortunate, is that the work done to generate a polynomial of degree n fit to the data. If you imagine now I add one additional data point, I might consider constructing a polynomial of one higher degree, right, which also interpolates all the data, including the new data point. But the work done to construct this polynomial of degree n using this Lagrange form of the interpolating polynomial does not, it's like simplify the task of computing Pn plus 1, right? Okay. And what we'll see, it's like later on, is that this leads to a different form of the interpolating polynomial, which is called the Newton form of the interpolating polynomial. The Newton form of the interpolating polynomial lends itself very naturally to a Horner type evaluation. And by its connection with what we call divided differences, it becomes a very easy process by which you can incorporate more data, for example. So we'll see a little bit more about that in a little bit. Okay, so let me just stop here for now. All right, and we'll carry this on a little bit.